It for today. So first off, a little review of what we talked about on Tuesday. Our topic is intermolecular forces, which again is the forces between molecules. And there are 5 types of intermolecular forces that we talked about, going from weak to strong. So the weakest is dispersion. All molecules, when they interact, can have dispersion interactions. Second type is dipole-dipole. This is available to only polar molecules. Then a special type of dipole-dipole is called the hydrogen bond. This is for polar molecules that have a hydrogen bound to a fluorine, an oxygen, or a nitrogen. Hydrogen is fun. Then we have the ion dipole. This is when you mix a polar molecule plus an ion. And 5, the strongest, is the ion-ion. This is between 2 ions, also called an ionic bond. The last topic that we talked about on Tuesday was looking at some properties. So the first property we looked at of intermolecular forces was solubility. Remember, the phrase we have here is like dissolves like. That is, polar molecules can dissolve other polar molecules. And the way we talk about that, the technical term is miscible. So polar molecules are miscible with other polar molecules. Polar and nonpolar are immiscible. Again, the reason for that comes down to intermolecular forces, right? If I'm a polar molecule, I get a lot of energy when I form dipole-dipole. So I want to interact with other polar molecules. Right. Any questions about that to start with? Right. So we're actually going to start right with a question that goes right off of question 4. Or sorry, goes off of solubility. So question 4. I have 4 molecules. And I'll draw out these molecules for you. Molecule 1 is N2. Molecule 2 is carbon tetrachloride. Molecule number 3 is carbon monoxide. And compound number 4 is silicon tetrahydrogen, or tetrahydride, I believe. The question is, I mix these 4 compounds together. Which one would be immiscible with the others? Would it be A, B, C, or D? So I'm going to give you about, let's say, a minute or so, get ourselves warmed up with the problem right away. Feel free, those of you in class, to talk it out. Those of you online, if you have questions, of course, you can always put it in chat. Otherwise, look back at your notes, see how we tell if something's miscible or immiscible with each other. All right, so that was about a minute and a half there. So remember, when it comes to dissolving substances, we really care to see what is polar and what's not polar. So this just becomes a game of who's polar and who's non-polar. And we talked about some of these tricks on Tuesday. If you are bound to yourself, well, you are non-polar. So N2 is non-polar. If you are carbon and if you are bound to for the same molecule, you are non-polar. If you're silicon and you're bound to for the same molecule, you're non-polar. When you have a carbon and oxygen bonded to each other, that is going to be a polar bond. So here, carbon monoxide is a polar molecule. The other three are non-polar, so C is the immiscible compound. It has a different property than the other three molecules. So carbon monoxide would separate from everything else. So that's our little review there about, just looking at these molecules, seeing what's polar and non-polar. Also remember that I put up a video, like a 15-minute YouTube video about polar and non-polar, and I put up a worksheet as well. So if the idea of seeing what's polar and non-polar, you don't quite remember that from Gen Chem 1, watch that video, go over that worksheet, and again, feel free to contact me and I can talk with you as well about that more. But any questions about question 4 here? All right, so our topic for this chapter is all about intermolecular forces, and specifically what we're going to focus in on is intermolecular forces in liquids. So IMFs in liquids. And really the question, or the thing we're going to look at, is how do the properties of liquids change? So how do the properties of liquids change based on the IMFs, the intermolecular forces? Because remember, chemistry is the subject of I want to understand how every type of matter in the universe behaves. I'm trying to understand that. And so IMFs, intermolecular forces, play a huge role in the behavior of liquids. And so the first property, so property 1 that we're going to talk about, is what we call surface tension. And just to give you a little real-world context of surface tension, so as I said on Tuesday, I grew up in Michigan. A fun fact about Michigan is that you're never more than 7 miles away from an open body of water, right? There's a lake or a stream at least 7 miles away from you, no matter where you are. And during the summer, like right now, what you would often see if you go to a lake is you would see little bugs running across that water, right? And they are so light, they can stand on water and not puncture it. That's surface tension. Surface tension is resisting being punctured if you're a liquid. So surface tension is resisting being punctured or your surface broken. And those of you who ever dived into a pool as a kid, you might also know surface tension. So if you're diving into a pool And the Olympics are coming up, so you're going to see this too. Which way would you rather dive into a pool? Would you rather dive into a pool with your hands forward or straight on your stomach? Your hands forward, right? Because if you go straight on your stomach, the surface tension punches you right in the gut because the water doesn't want to be broken. You feel that. If you go with your hands, you're breaking that surface tension with all your force at one point. So it's a lot easier for the water to be broken. This all comes down to surface tension, right? Because let's take water, for example. So I'm going to draw out water. Okay, so what is the strongest intermolecular force that water has? I think I just heard it. The strongest IMF water has available to it is the hydrogen bond. And so at the surface of water, you have all these water molecules that are hydrogen bonding to each other. In all directions. So you have this giant web of hydrogen bonds. And above the water, right, you have air. Now, I had this in my slides, but does anyone know what molecule makes up the majority of the air that we breathe? It's nitrogen, N2. So 78% of what we breathe is actually nitrogen. N2 is nonpolar. And like we just talked about when it comes to solubility, these two things don't want to mix, right? They don't want to interact. So they don't want to mix. And so that is the idea behind surface tension. If I puncture the surface of water, basically what I'm doing is that I'm making like a little divot in the water and air goes in there. And water, at that point, more water has to interact with N2. And water does not like that, right? Because it can no longer hydrogen bond. So resist that. That's the force you feel if you try to jump into water and you belly flop. You just hit it with your belly. Because you are trying to break all these hydrogen bonds and force them to interact with N2. The water says, I'm going to try to resist that as much as I can. I'm going to push back against you. That's the force you feel when you hit water. And that happens in any liquids. And so generally, this is an idea of intermolecular force. Water has very strong intermolecular forces, and it has strong surface tension. And the key thing here is that the stronger the intermolecular forces, the stronger this surface tension. That is, the harder it is to break the surface of this liquid. So if you had a pool of gasoline, which is generally nonpolar, you try to do a belly flop in that, you'd probably go right in and not hurt all that much because there's not much tension there. Water, though, yeah, it does not like to break. So that's our first property. Any questions about surface tension? Yeah.
Say you like go through like honey, super thick.
Yep.
You were to belly flop, somewhat giant.
If you,
Would you potentially die?
If you're high enough, yeah, for sure. If you jump, like, if you jump off a very tall bridge into water, you're probably going to break your neck, right? Unless you do that Olympic dive, if you just hit it like that, you're dead because you're hitting concrete. Honey would be even worse. Because imagine jumping 10, I can imagine jumping 10 feet off into honey. You might like hit it and then bounce back a little bit, then slowly sink in and drown. So yeah, you'd probably break bones. Anything else? All right. So I do have a question for this. This chapter is all about determining what intermolecular forces are present in a molecule. So question 5, you have 2 molecules. You have acetone. And remember, anytime I write these little lines next to carbon, those are hydrogen. You have acetone versus water. My question is, which has the highest surface tension and why? So I'm going to give you, again, like a minute to think about this, reviewing your notes, see if you have any questions. Feel free to talk amongst yourselves. Those of you online as well, feel free to put questions in the chat. Just make sure I didn't take chat. All right, so that was a little bit over a minute. So the way to be successful for this first part of the class is really looking at molecules and using some of the tricks we talked about on Tuesday to determine the intermolecular forces quickly, right? That's what we want to do. And so let's look at our 2 molecules. So what I look at when I see these 2 molecules is I'm looking at our different types of interactions. So I have a carbon-oxygen bond. Whenever I see carbon and oxygen bonded together, I immediately think that's polar. I have a carbon-carbon bond. Whenever 2 molecules are bonded to each other and they're the same thing, I think to myself that bond is nonpolar. And I have a carbon-hydrogen bond. Carbon-hydrogen is something you see a lot, especially those of you going to organic chemistry. That's what organic chemistry is. So when we see carbon-hydrogen, we also think that's nonpolar. So we have a polar bond. That's going to be our strongest intermolecular force. There's no hydrogen attached to my oxygen. So the strongest intermolecular force that acetone has is simply dipole-dipole. By the way, acetone has many uses. The use I always say is that when you're walking in like a mall and you go by the nail place and you get hit with that smell that makes you dizzy, that's acetone. Yeah, it's good at removing nail polish and other nonpolar substances. Water, we talk about it a bunch. We have oxygen and hydrogen bound together. When you see that, you should think hydrogen bond. A hydrogen bond has a stronger intermolecular force than dipole-dipole. Therefore, water has a higher surface tension. So that's how I want you to start tackling these problems. Look at the molecule, see what is bonded to each other, and start asking yourself, what type of intermolecular force might I expect from that bond? Right. Any questions though about that question or surface tension now that you had a moment to think about it? Okay. So property 1, surface tension. Oh yeah, what's up?
So if they have the same type of bond, like both of them have hydrogen bond.
Yep.
Would that then rely on like the shape and then size?
Shape and size. It's mostly going to be size when you talk about, well, it's both. All hydrogen bonds are not made the same. There's different strengths based on how things are bonded. You can make a hydrogen bond stronger or weaker. You can make a dipole-dipole stronger or weaker. So yeah, you would have to look at, generally it comes down to what's bigger, but it doesn't have to based on the chemistry. That being said, I wouldn't give you the question of here's two things hydrogen bonding, which one has the highest surface tension. I'm more interested in, do you know what a hydrogen bond looks like? Do you know what a dipole-dipole looks like? If you get to higher levels of chemistry, that's when that stuff comes into play. Right now, we're just looking at the intermolecular forces. Yeah.
Will the stronger hydrogen bond like when there's multiple of the electrons?
Stronger, you can create. Hydrogen bond really doesn't depend on that, because a hydrogen bond is simply, it's always going to be like one hydrogen. I mean, you can have multiple hydrogens, sure. What makes a hydrogen bond stronger is when it's interacting. Again, we are now going into the world of physical chemistry here. You are looking at basically distance and orientation. Because when we talk about hydrogen bonds, it's interacting, intermolecular force. So based on my partner, based on what direction they're facing and how close or far they are, modulates how strong my interaction is. That's very important when it comes to things like proteins, and those of you who are interested in pharmacology, that's very important when it comes to making drugs. Because you can modulate how strong your drug binds to your target if you know what your target looks like. Oh, I can put an OH group here because I would make a hydrogen bond here. According to my calculations, that would be strong. So that's how we modulate. You can do two things. You can think about this, or you can just put a bunch of hydrogen bonding groups right next to each other. That's how DNA works. DNA, when you have your bases come together, one pair of bases, your G's and your C's, you form 3 hydrogen bonds. A's and T's form 2, and that modulates strength as well. So that's what we look at. How many and direction. But that's all an aside. Anything else? All right. Property 2. Viscosity. And viscosity is basically resistance to flow. And since we already talked about honey, let's talk about honey as our example. So imagine I have 2 liquids. One liquid is honey. The other one is water. And imagine I had these 2 things in my hands. I pour them out. Which one's going to come out faster, the honey or the water? The water, right? Because we would say honey is very viscous. So viscosity means how slow you are to move, resistance to flow as a liquid. The reason why, well, let me ask you, what molecule makes up the majority of honey? What's sugar? What's the molecular name of sugar? Glucose. Yeah, it's a lot of glucose. And I'm going to butcher the structure of glucose. It basically looks like that with all these OH groups. So this kind of gets on what we just talked about. Glucose has a ton of hydrogen bonds. So when two glucoses come together, they stick together really well. So they have much higher intermolecular forces, much stronger intermolecular forces than water, which only has 2 hydrogen bonds. Well, technically water can form 4, but glucose can form a lot more because it has a bunch of OH groups. And so when we think about viscosity, the stronger the intermolecular force, the higher the viscosity. However, we can influence viscosity. We can change it. So again, let me put forth this question. Imagine that it is, it's January here in San Antonio, and it's one of those rare days when we wake up and it's like 30 out. Okay, it's very cold out. I want my breakfast to have honey on it. I want some toast and honey. However, when I squeeze my little bear, it's kind of stuck in there. If that was the case, what would you do to make it come out faster? Heat it up. Yeah, so one thing that influences viscosity is temperature. So the higher the temperature, the lower the viscosity. And we can briefly talk about why that is. And this is a topic from Gen Chem 1, which I'm also teaching in the summer, and we actually just talked about this, so a little bit of a review. Higher temperature means more energy. There's more energy around if the temperature's high. If there's more energy, therefore, it's easier to break bonds. And so when a liquid is moving, you are breaking bonds. You're breaking its intermolecular forces. That's how it's moving. And so the hotter it is, the easier it is to move. So our second so temperature is 1. The second way we can influence this is shape. And you actually already all know this. Well, I don't even know how to ask this because it's kind of obvious once you think about it. What shape is the best for moving something? A sphere, right? So the more sphere-like your object is, the lower the viscosity. So if your molecule looks like a circle, it's going to be less viscous than something that looks like a line. This also ties back to intermolecular forces, though. The more linear you are, the more interactions you can have because you have more surface area. But you can also think of it as like car wheels. Car wheels are a circle for a reason because that's the best shape for moving. So that's our second property, viscosity. Any questions about that? Right. Let's move on to property 3 then. Property 3 is capillary action. Capillary action is simply a liquid moving up a tube. So it is simply if I have liquid here and I put a narrow tube in that liquid, what will happen naturally is that liquid will climb up the tube. That is what capillary action is. Liquids going up a tube against gravity. And so to understand this, let's zoom in. So that's what my picture right here is going to be. So I'm going to take this tube and I'm going to zoom in to see what is happening chemistry-wise. And again, we're going to have water. So of course, water's interacting with itself. And so in capillary action, the first force we're going to talk about is called a cohesive force. That is simply your liquid-liquid interaction. But the liquid isn't just interacting with itself, it's also interacting with the tube. And so that's our second interaction. This is called an adhesive force. This is your liquid tube interaction. So now that we have defined those two, let's talk about why capillary action happens. I stick a tube into a liquid. Because of adhesive forces, the liquid wants to interact with the tube. So it's going to start climbing the tube to interact with the surface, right? Everyone's like, ooh, new interactions, let's go interact. The liquid in the middle of that tube gets pulled up with the liquid that's climbing the tube because of cohesive forces. As everybody is climbing the tube, those ones in the middle are saying, where are you going? You're taking my hydrogen bonds with you. I'm gonna follow you. And so it climbs up the tube as well. That is what's going on there. It's a mixture of cohesive and adhesive forces. Now, let's kind of think about this for water. In lab, when you look at water in an instrument, which way is the meniscus? Does the meniscus curve like a smiley face, or does it curve like a frowny face? It's a smiley face, right? The meniscus looks like this. That's what we call the meniscus. All right. From what I just told you, does that mean when water interacts with a tube, what is stronger, adhesive forces or cohesive forces? Adhesive, right? That's why you get the little smiley. The water molecules at the side are climbing even higher. They're trying to reach as much tube as they can. But the ones in the middle after a certain point, gravity is saying it's pushing down too much on the water that they don't have enough energy to climb anymore. The cohesive forces are no longer strong enough to resist gravity. So once you get this meniscus, that means the gravity, the force of gravity, is stronger than your cohesive forces. And up here, that's what's also happening. The force of gravity is now stronger than your adhesive forces. That's why the water stops climbing. However, since we have a meniscus that looks like a smiley face, that means that the water in the tube has a little bit more energy. They can climb a little bit higher. Not all liquids work this way, by the way. The classic example of something being opposite than this is mercury. Now, unfortunately, you all and myself, we were born too late. Back in the 50s and 60s, once you hear those old professors talk, they talk about when they were in school, professors would give them mercury to play with in their hands, right? Which isn't great, but yeah, you got to play with mercury. Now, good luck finding mercury in this university. However, if you were going in science in the 60s, you would see a mercury meniscus. It looks like that. The meniscus is opposite from mercury, which means for mercury, the cohesive forces are stronger than the adhesive forces. And it all comes down to the shape of that meniscus. So that's our third property. Right. Let me zoom back out. Any questions about capillary action? Yep, exactly. Yeah. So if I had a thing of mercury in a bottle and I threw it on the ground, it would form little beads and roll all over the place. Yep. It does not like spread out like water. It wants to, yeah, that's just what it does. It forms little circles. Yep. Yeah.
And then when it something like it does want to push out of it.
Well, adhesive, yeah, that exactly is why we use that word for like tape, right? Because it sticks to something else. Adhesive is two different things interacting. Cohesive is you're interacting with yourself. So adhesive is I'm interacting with someone else. Cohesive is I'm interacting with myself. We're a cohesive unit. We work together.
That kind of thing, like what you're adhering.
Yeah, you adhere to that policy, right? It's somebody else's policy that I'm sticking to, right? That's where, yep, that's where that language comes from. Anything else? All right, I got a simple question for you, but something you might see when it comes to testing. What would I ask you? Question 7. I got 2 molecules. 1, 2, 3, 4, 5, 6. This molecule that I just drew out is called hexane. And we're going to put that up against water. So my question is, which of these substances would climb higher in a tube? So I have hexane and I have water. And I'm just going to give you, this one I'll probably only give you like 30, 40 seconds collect your thoughts, look back at the notes. Yeah, anytime I write little dashes next to the carbon, that means a hydrogen is there. Yep. All right. So again, whenever we're looking at molecules, you're asking yourself, what are the intermolecular forces present? And the way to do this to start, which is where we're at the starting ground of just looking at these molecules. You want to take each bond by itself. Look at the different types of interactions. So in hexane, you only have two types of interactions. You have a carbon-carbon bond. Again, if a molecule is bonded to itself, that is nonpolar. These dashes are hydrogen. And this is just something you kind of want to know. A carbon-hydrogen bond is also nonpolar. So hexane is a nonpolar molecule because it only has nonpolar interactions, nonpolar bonds. So the only intermolecular force it gets is dispersion. Water, the reason why we use it so much is because, we're 70% water. Water is everywhere. So it's a great thing to use as our test subject. Again, we see hydrogen, oxygen in a bond. That means, you get a hydrogen bond. When it comes to cohesion and adhesion, the stronger the intermolecular forces, the higher you climb. So the stronger the IMFs, the higher you climb for capillary action. Yeah. Yeah, so I'll repeat that question. So the question was, if it's nonpolar and there's no ions, it's only dispersion. Even if there were ions, it's only dispersion. Nonpolar only gets dispersion. That's all it gets. It is weak. That's the weakest force. But that's what nonpolar gets. Yep. So as long as you see nonpolar, that's your answer. Dispersion. Yeah.
So if you mix some like salt
Mm-hmm.
to make like a stronger bond, it would quantify.
I don't know if it would, because when you add salt to the water, the stronger interaction is between the salt and the water. When you're talking about adhesive forces, that is still between the tube and the water. The salt isn't playing any part in that, but I'm not 100% sure. Salt water might climb higher. I actually don't know that off the top of my head. My gut would say it would be roughly the same because it has to do with adhesive forces, and that's still water though. Now, if you had liquid salt, like molten salt, that thing would climb probably super high. It would also melt the tube, but it probably would climb high. All right, anything else? All right, so let's do maybe one or two more properties and then we'll take our halfway point break here. Property 4. Vaporization. Vaporization is simply taking your liquid and making it into a gas. So I have a question, might seem a little bit obvious, but I'm going to ask it anyways. To vaporize something, do I put heat in or do I take heat out? You put heat in, right? If I want to boil water, heat goes in. So heat goes in. All right. So if I'm putting heat in to make a gas, am I breaking intermolecular forces or am I forming intermolecular forces? Yeah, you have to break them, right? That's what heat does. Just like when we talked about viscosity, more temperature means it's easier to break IMFs. Okay, so when it comes to vaporization, we want to remember those two things. I have to put heat in because I need to break intermolecular forces to make a gas. So, my question for you, the stronger the intermolecular forces, do you think then the stronger my intermolecular forces are, is it harder to vaporize something or is it easier to vaporize something? It's harder. Yeah, exactly. Right. That's the logic of this. So my higher my intermolecular forces, the higher we measure this by boiling point. Right. The boiling point is, let's just define that, the temperature at which a liquid becomes a gas anywhere in the liquid. And I'm going to underline that anywhere. Because I forgot my water today, so I'm going to be using Dr. Pepper as my example. So let me turn my camera back on because this example does have a prop. So for this bottle of Dr. Pepper, right now, is this vaporizing? And it might surprise you to think, but yeah, it is. Because imagine I had this bottle of Dr. Pepper and I have the cap off. I put it in my office and I come back after 6 months. Is there any soda left in that bottle? No, it's gone. Did my office ever get to the boiling point? No. So liquids are vaporizing all the time. That's what they do. However, the boiling point is it can become a gas anywhere. Right now, the only part of this soda that's vaporizing is the very top. So at the very top, some of that liquid is becoming gas. It just is. At the boiling point, and you see this if you cook, gas bubbles form anywhere in this bottle, anywhere in the pan. That's the difference. The boiling point is it can become a gas anywhere in the liquid. Keep in mind though, liquids can vaporize at any temperature. It's just at the boiling point, they'll do it anywhere in this whole volume of liquid, just not at the surface. Any questions about that idea? All right. I just want to throw out a little bit of vocab for you. We have some scientific terms to talk about this. And that's volatile, and non-volatile. So volatile simply means you vaporize easily. And I'm going to use nail polish as my example there. Because if you open up a bottle of nail polish, you get hit with the smell right in your face. That's because it becomes a gas very easily. And that's what you're smelling. You're smelling gas. While non-volatile is the opposite. Doesn't vaporize easily. Honey can be a good example there. Honey doesn't turn into gas that easily. You can leave honey uncapped and it might grow. Well, actually it won't grow bacteria because there's a lot of other chemicals in honey naturally that prevents that type of growth. But it won't vaporize because it's very sticky. It's non-volatile. So that's our terminology. Volatile, you have weak intermolecular forces, you vaporize easily. Non-volatile, strong intermolecular forces, you don't vaporize easily. Honey has a very high boiling point, by the way. Questions about vaporization? Right. Our last property, then we'll take a short break. It's the opposite. It is condensation. So let's say that for some reason, either yesterday or Tuesday, when the heat index was 118 and 112 respectively, it was a little bit hot out, you decided to eat outside in the sun. And so you go to a restaurant, they bring you a nice tall glass of ice water. What's going to happen to the outside of that ice water pretty fast? It's gonna start, as we used to call it, sweating. It's going to get a lot of water on the outside. Where's that water coming from? Is it coming from inside the glass? Coming from the atmosphere, right? What is happening is that the water vapor in the air hits the side of the glass. It cools down because it's now touching something cold. And since it's colder now, it can form new intermolecular forces. It goes from a gas to a liquid. We do that by removing heat to form intermolecular forces. So just to go back, vaporization and condensation are completely opposite of each other. One, you add heat to break intermolecular forces. The other one, you remove heat to, I don't want any notes, quit it. There. You remove heat to form intermolecular forces, right? And so this is gonna go the opposite. Well, it's not quite opposite, but it's basically the stronger the intermolecular forces, the easier to condense. And it's the opposite, but it's hard for me to use the same like higher or lower. But for vaporization, right, we said the higher the intermolecular forces, the higher the boiling point. Another way to think about this is if the boiling point's high, that means I want to be a liquid. I don't want to be a gas. And so condensation is saying the same thing. It's easier to condense, which means I want to be a liquid. I don't want to be a gas. And nonpolar molecules are the opposite, right? As we just talked about earlier today, 78% of the thing you're breathing right now is nitrogen gas. Nitrogen is nonpolar. To make it a liquid, you have to go to like minus 200 Celsius. It has to be incredibly cold because it has no intermolecular forces other than dispersion. So it doesn't want to be a liquid. It doesn't get anything out of interacting. Polar molecules are the opposite. They have strong intermolecular forces, and so they want to be a liquid. So that's our last property for intermolecular forces in liquids. Any questions about NR5 properties? I'll just do a quick review, refresher here. So the 5 properties were, let's go to these again. Surface tension, higher intermolecular forces, higher surface tension. Viscosity, higher intermolecular forces, higher viscosity. Capillary action, higher intermolecular forces, the higher the capillary action, the stronger the adhesive forces. Vaporization, the higher the intermolecular forces, the higher the boiling point, harder to vaporize. Condensation, saying the same thing. Condensation, the higher the intermolecular forces, the easier you are to condense. Questions about that? All right, we are roughly at the halfway point. So it is 9:02. Let's take an 8-minute break. And let's return to 9:10. Get your calculators out, because when we come back, everyone's favorite, math. Let's put numbers to things. Yeah, what's up? Well, that should be eligible for more, so I can double check. It might be the wrong there. Yeah, I checked that. And we want to talk about just the water. What? Yes. Alrighty. Let's get back to it. I'm gonna open up a new sheet so the thing doesn't happen on Tuesday where I reach my limit. Yeah. So we've been talking about intermolecular forces and we've been talking about these 5 properties. And chemistry not only seeks to understand matter, but ultimately we want to make predictions, right? That is our power as chemists. We want, and as humans, really shaping the world around us. And so we're going to put numbers to this to really understand how to influence things. So what we're going to talk about is the heat of vaporization. Basically, the heat of vaporization is how much energy do I need to vaporize 1 mole of a liquid? And since this is the first time we talked about this unit, just as a reminder, a mole is just simply a lot of atoms. That's all it means. Technically, it's 6.022 times 10 to the 23 atoms. That's Avogadro's number. We most likely won't use that number this semester, but it's just a lot of stuff. The symbol for heat of vaporization is delta H vac. And so let's briefly talk about what those letters mean, because we're going to see them quite a lot this semester. So that triangle, the way you pronounce that is delta. Anytime you see that, the translation is change. You are looking at a change. That's what delta means, change. Usually when we talk about delta, we are looking at final state minus initial state. So for us, the final state is gas. If we're vaporizing something, the initial state would be liquid. Honestly, that doesn't apply to us really, because we're not going that in depth into the theory, but we will this semester look at delta and use final minus initial. So I'm introducing that to you. When we see the capital H, that means enthalpy. That's the technical term for that. The way I describe enthalpy is heat energy. All right, so if we take these 2 definitions and we look at our symbol, if I was to say this in English without the technical terms, it would be the change of heat needed to vaporize something. Or how much energy do I need to vaporize something? All right, so as we just talked about before we went for our break, do I put heat in to vaporize something or do I take heat out to vaporize something? You have heat goes in. So, with that in mind, do you think delta H VAP would be a positive number? Do I have, yeah. Would it be a positive number or would it be a negative number? positive because heat goes in, right? So delta H vaporization is always a positive value. And now let us tie this back to intermolecular forces, because that's our main topic for the first part of this semester. So the stronger the intermolecular forces, is it easier or harder to vaporize something with strong intermolecular forces? Is it easier or harder to vaporize that? It's harder. So is heat of vaporization higher or lower for things with strong intermolecular forces? Does it have a high heat of vaporization or a low heat of vaporization? High. There you go. You got it, right? That's the logic we follow. The higher the intermolecular forces, the higher the value of delta H vaporization. The more energy I need to put in to vaporize something. In delta H vaporization, and this was brought to my attention that on our pre-class assignment, I picked the wrong option, but it does have units of kilojoules per mole. And one of the things that I would love for chemistry students to be able to do, look at these units and translate them, right? And what I mean by that is that joule is a unit of energy. So really what this unit is saying is how much energy I need for every mole of substance, and mole is just a lot of atoms, to do a process. The process we're looking at is vaporization. So these units are saying how much energy in joules do I need to vaporize 1 mole of substance? The stronger my intermolecular forces are, the more energy I need. That's why that value goes up. Since I'm putting heat in, that is a positive value. All right. Any questions about the definition of heat of vaporization? All right. All you mathletes, mathaholics, mathologists, we're going to start with an easy one. Don't worry, we'll get more complex as the semester goes. Question 9. I have 250 grams of H2O. Don't worry, soon enough we won't use water as our example for everything. The molecular weight of water is 18.01 grams per mole. The delta H vaporization of water, which has a unit of kilojoules per mole, is 40.7. The question is, how much energy do I need to vaporize this water? So I'm going to give everybody a few minutes to figure out this calculation. Remind yourself how you convert from grams to moles. One thing I want you to start doing in this class is figure out what your ending unit should be. Now I'll help you out the first time. The question is how much energy. So your ending unit should be a unit of energy. So your goal is to end in a unit of kilojoules. Right? Right now, delta H vaporization is kilojoules per mole. You want to cancel out that mole. So I'm gonna let you struggle with this. I know we haven't gone over it yet, but the best way to learn is to struggle. Feel free, those of you in class, talk amongst yourself. I'll do a lap or two. Those of you on the Zoom call, if you have questions with this, feel free to send me a message. But yeah, see if you can figure this out. I had to do that. Well, one thing I would suggest, I bring you right down, number put next to them. Because that's what just something that's.
Okay. I also.
It's gonna take you a lot more. You don't have to do the train tracks, but just for dumb. Always have our numbers, always have your units available. Alrighty. So you have some time to think over how to do this. Even if you didn't finish, that's all right. Just getting it in your head. This is really a Gen Chem 1 problem with one added step. So the flow of what you're doing is that you start with grams and you want to convert that to moles. And then once you are in moles, you can multiply that by your delta H and you'll be left in a unit of kilojoules. This is why I want to stress so much about understanding units and how they cancel. Because I never give you a formula to do this. There is a formula, and the formula it's very simple. It's simply delta H times moles gives you kilojoules. However, the majority of the calculations we do in this class, you don't need a formula if you know how units cancel out. There are some equations you need a formula, you just have to. But this, you can figure it out. And the way I do all my calculations is what are called train tracks. It's just unit conversion. And so I start with 250 grams. I'm gonna start with that because that's what I was given. And in my flow chart, I want to go to moles. That's the first thing I want to do. So in these train tracks, the way it works is that if there's any unit on the top and bottom of these tracks, they cancel out. And so what I'm doing is I'm taking my weight and I'm dividing by my molecular weight. I'm just doing it in a way to keep it organized for myself. So when you take your molecular weight your weight divided by your molecular weight, your unit is now moles. However, I want my unit to be kilojoules. So I need moles on the bottom to cancel out moles. And I'll be left with kilojoules up top because that's what delta H vaporization is. Delta H vaporization says for every 40.7 kilojoules of energy, I can vaporize 1 mole. And the way this system works, you multiply everything on the top divided by everything on the bottom. Like I said, you don't have to do it this way. What I'm doing basically is I'm taking my 250 divided by my molecular weight multiplied by delta H. These two are saying the same thing. I just can't. I have trouble thinking about it in the terms on the right. I need the crutch of looking how the units cancel for myself. So what I'm going to do on my phone calculator, once I pull up that app. Oh, and those of you, everybody who's calculating, please try to use the calculator you're going to use on the test. There's a lot of times people, when it comes to test time, they use a different calculator and they get flustered. Always use the same calculator. So I'm doing 250 times 40.7 divided by 18.01. And the answer, I'm just going to double check that. No, that sounds right. The answer is 564.96. If we want to go by sig figs, I have 3 sig figs. So rounded, that would be 565 kilojoules. So that's how much energy it takes to vaporize 250 grams of water. Takes a lot of energy, 565 kilojoules of energy. Right? Questions about calculating delta H vaporization for us? All right. So going back on what we talked about earlier, vaporization and condensation are opposite. And for opposite processes in chemistry, and this is true of any opposite process, the value of delta H vaporization is equal to negative delta H condensation. We see expressions like this all the time in chemistry. And that I know this type of expression can confuse you if you're not used to looking at it. So what this means, so delta H vaporization for water is 40.7 kilojoules per mole. Delta H condensation for water, what this says is that it's equal to negative 40.7 per mole. So what this expression says, delta H vap and delta H condensation, they are the same value, but opposite signs. Delta H vaporization is always positive. Delta H condensation is always a negative value. Which makes sense, right? Delta H vaporization, we say we put in heat, so that's why it's positive. And we said to condense something, we take heat out. That's why it's negative. However, since these are opposite processes, the energy you need to put in and the energy you need to take out are the same. You're just doing opposite. You're either putting it in or taking it out. So for almost, I want to say any opposite process in chemistry, this behavior holds. that opposite processes have the same numerical value, but opposite signs. Yeah. Hmm? So basically what's happening is that when the gas hits the glass, you have a hot thing coming in contact with a cold thing. When two things are at different temperatures and they touch, they try to become the same temperature. So the heat in the gas goes into the glass. So that's where it's going. However, the glass of water is massive, so that doesn't change temperature that much. It does some because you see the ice cube start to melt. That's what's happening. But the gas is so tiny that it loses like all of its heat and becomes the same temperature of the water inside pretty fast. That's where the heat's going. That's also just along that line. Since we're talking about water, that's why we sweat when it gets hot. When you sweat, you put liquid water on your skin. The heat from your body goes into that water because they're different temperatures and it becomes a gas. That's why it cools you off. Any other question? All right. Terminology time. This is back from Gen Chem 1, but we use this terminology in Gen Chem 2 as well. So very simple question 10. Is evaporization endothermic or exothermic? So I want people to think about that for like 10, 15 seconds. Remember what those terms mean. Is it endothermic or is it exothermic to condense something? Or sorry, to evaporate something, to evaporate. All right, so those of you that I can see, if you think evaporization is endothermic, just show me number 1. If you think it's exothermic, show me number 2. What do you all think? Very good. Yep. So remember, endothermic, the way I remember that is heat goes in. Exothermic, the way I remember that is heat goes out or exits. So to evaporate something, we have to put heat in. That's why it's an endothermic process, right? And that goes along. I actually kind of gave you the answer when I talked about sweating, right? When you sweat, the heat from your body goes into the water. So you evaporate that water. It's an endothermic process. You are the heat source. That's also why if it's cold out and you get wet, you're going to die pretty soon because all the heat leaves your body to go into that water and it's already cold out. So you are in big trouble. Very bad to be wet when it's cold. All right. But any questions about vaporization, condensation? All right. I'm just looking ahead to see what's ahead of us. Okay. So we're gonna talk, we're gonna briefly step away from the math. I'm sorry, mathletes, we'll be back, I promise. And we're gonna tie this idea of gases with vapor pressure. Because this idea of vapor pressure goes along with vaporization and condensation we were just talking about. So first off, let's define vapor pressure. And to do that, we're going to think of a system. So this is our sealed system. So you can think of a glass or Hey, a soda bottle. Right now, this is a sealed system because I have the cap on. Inside my system, I have liquid and I have a gas phase. So I asked the question earlier, if I left this soda bottle on my desk, we can use our prop again. If those of you at home, you want to see me hold my delicious Dr. Pepper, not sponsored by the way, but very good. I said if I left this on my desk with the cap off, we all agreed if I left it there for 6 months, it would be gone. Okay, same question, but I left this bottle on my desk with the cap on for 6 months. When I come back, will there be soda in there? Yeah, because it has nowhere to go. And that's kind of the idea of vapor pressure. With the cap off, it disappears. Why does it disappear again? It's becoming a gas, and then the gas leaves the system. In a sealed system, and the correct terminology is closed. It's a closed system, not a sealed system. In a closed system, the same thing is happening. The liquid is becoming a gas molecule. So that's still, you still have vaporization happening there. However, since this is closed, that gas has nowhere to go. And so eventually it will go back into the liquid. And you'll have this cycle happening where some liquid becomes a gas, some gas goes and becomes a liquid. Eventually, you'll reach this place called equilibrium. Equilibrium is something we will talk about, I don't know, probably like 3 weeks from now. We'll talk about equilibrium a lot. But right now, what I mean equilibrium is the rate at which your liquid becomes a gas is equal to the rate at which your gas becomes a liquid. Right? So I'm becoming a gas and the gas is going back at the same speed. What that means is if this is true, the concentration of gas doesn't change anymore. Because if the rates are the same, the amount of gas in your system is fixed. It is a constant. All right. And from Gen Chem 1, see if you can remember this. I know it's been a while for some of you, so let's go back to our memory banks. How do we measure the concentration of a gas? The answer is already on the board, by the way. Pressure. Remember, for gases, we generally measure the concentration of a gas via pressure. Right? And so if you were going to ask what is the concentration of gas in my tires on my car, you would measure that in PSI. That's the measurement of pressure. So the idea of vapor pressure is when you're at this equilibrium, the concentration of gas doesn't change, which means the pressure of gas doesn't change. All right. And let's tie this back to intermolecular forces, because that's our big thing here. All right. So if you have high intermolecular forces, based on what we said today, do you want to be a gas or would you rather be a liquid? if I have strong intermolecular forces. You want to be a liquid. So the higher the intermolecular forces, the higher the boiling point. Right? And that's kind of how we measure that, right? We measure boiling point. That tells us strength of intermolecular forces. Okay. So we have that in our mind. So if I have strong intermolecular forces, do you think I have high vapor pressure or do I have low vapor pressure? You have low vapor pressure. And again, let's just talk about that logic again. In a closed system, you're going to have some concentration of gas that doesn't change. This is called vapor pressure. If you have strong intermolecular forces, you'd rather be a liquid than a gas. So the majority of you will be a liquid. Therefore, if you have strong intermolecular forces, you have low vapor pressure. Using our terminology, the more volatile, remember volatile just means you want to be a gas. The more volatile a liquid, the higher the vapor pressure. So honey has like no vapor pressure. It's not volatile. Gasoline has very high vapor pressure because it has very weak intermolecular forces. If you leave a gas canister outside in the sun, it balloons up and eventually will pop the lid because the vapor pressure gets so high in it. But if I had that gas canister full of water, it would be just fine because it doesn't have nearly as high as vapor pressure. All right, any questions about that? And I'm going to add one more thing to that. How to change vapor pressures. And again, I'm just going to be very clear. The vapor pressure is the concentration of gas in a closed system. That's what it means. Those of you who look at weather often, you'll see that we measure vapor pressures in the world too, right? Because you can kind of think of Earth as it's not a closed system, but for water vapor, it kind of is. Water vapor is going to have a hard time going into space. A little bit would, but how can I change the amount of gas in my closed system? And so we just talked about that. If I increase temperature, so the higher my temperature, the higher my vapor pressure. And again, I will go back to that example of gasoline in one of those canisters. Because back when I was college aged, I don't have the most common sense in the world. I still don't. And so I filled up one of those because I ran out of gas while driving, of course. I wasn't that far from a gas station though. So I bought one of those and then walked back to my car. However, I still had some gasoline left in there. I didn't pour it all out and I just threw it in my trunk. Of course, that's what you do. And then after a couple of months, I opened up my trunk again. That thing ballooned. It was just whoop, and the top popped off. because all the gas that was left in there inside my trunk got very hot. The vapor pressure started to rise as all that liquid became gas, and eventually that gas was enough to pop. I'm not going to go there. I guess it's kind of like the same idea with a bomb. Not quite, but like in those pressure cooker bombs, you have a sealed environment and you just raise the pressure and it will eventually explode. It's kind of like the same idea there. But yeah, that's how we can change vapor pressure, temperature. So two things influence it: intermolecular forces and temperature. Yeah. Recapping champagne. I don't know about it. So the thing with like champagne and stuff like that is that you have gases dissolved in the liquid. And gases don't dissolve in liquids that easily. And so I think the idea is when you originally cap it, you put the cap on so strongly that it's able to resist the vapor pressure. However, if you uncap it, all that gas can now leave. And that's why you can shoot off those things like super strong. However, if you try to recap it, I think you can't do it as well as it was originally capped. And so the gas will eventually push it out, I think. If it's at room temp, you're releasing more gas. Yeah, and that's not vapor pressure per se. That's solubility of a gas. That's a slightly different topic. When I'm talking about vapor pressure, I'm talking about the liquid itself. Yeah, for champagne, that would do with dissolved gases. The colder the champagne is, the more gas. No, it's the opposite. It's actually the hotter it is, the more gas you can dissolve. The colder it gets, the less gas you can have in there. But it's a slightly different topic. It's a similar idea though. All right. Any other questions? Yeah.
So it kind of deals with what was it like the boiling point thing.
Mhm.
So I understand that once something gets to boiling point, any part of it can above gas.
Yep.
So why does soda bubbles not boil?
That's carbon dioxide. All right. It actually goes right along with the champagne. To make this fizzle, make sure this on really tight. That's all carbon dioxide that you're seeing. That's not gas, liquid water. Carbon dioxide is nonpolar. It doesn't want to be in the liquid. So if I shake this up, I'm allowing that carbon dioxide to leave the water, and it goes inside the gas phase, and the pressure builds and builds and builds. And when you open it, if this was full, as you all know, I'm sure, it would all gush out because you have released so much carbon dioxide. You have just opened a closed system and it says freedom, and some of the water just goes with it because the force of it is so high. That's what's going on there. So again, that's solubility of a gas, which is something we're going to talk about actually pretty soonish, next week, some point, I think. Oh wait, no, we talked about that in Gen Chem 1, I think. So never mind. Oh no, it's there. It's there. Yeah, it might be next week. I have to remember our topics. Yep.
It's a mix. That's a mix.
It's a mix of different, like, because a lot, we put ethanol in our gas now because of like farm bills. So it is a mix of like some different compounds, but they're all pretty non-polar. Yeah.
It's not part of the gas. It's something.
It's the liquid itself becoming the gas, because that stuff is generally non-polar. Ethanol is a little bit polar, but most of the gasoline we use, oil, is non-polar. So the intermolecular forces are dispersion. So it doesn't want to be a liquid all that much if it doesn't have to be. So when you have a closed container, you get high vapor pressure. You know this at the gas station. You know, every time you take the pump out, a few drips always drop on the road or on the ground, and it just immediately evaporates because it doesn't want to be a liquid if it doesn't have to. The reason why it stays a liquid in your car is that it's basically like a closed system. It doesn't have anywhere to go, so you'll get that equilibrium of liquid and gas at that point. Same as when it's underneath the ground at the pump. It doesn't have anywhere to go, so you'll get an equilibrium. And it's not that bad that it would be like a bomb situation. The vapor pressure isn't that high for what we use, but some of it will be in the gas form. Yeah. So if you have uncapped nail polish in your car, when you open up your car, you're probably going to get dizzy super fast because all that will become a gas and you just stay in your car and go hit with that smell. Yep. Anything else? All right. Now I have to go back to what slide I was on because I just jumped ahead like a week and a half. All right. So let's talk about, okay, my math people, we're back. Let's talk about how we measure delta H vaporization. Because in my previous problem, or in my previous examples, I always gave you delta H vaporization, right? Water is 40.7. However, somebody eventually in the past had to figure that out. So how do you figure that out? You figure that out via vapor pressure. What you do experimentally, you have a solution and it's a closed system. So this is my liquid closed system. You measure vapor pressure as a function of temperature. So it's actually a pretty simple experiment. You have your solution at a certain temperature, measure its vapor pressure. Change the temperature, measure the vapor pressure. Change the temperature, measure the vapor pressure, so on and so on and so on. And this was all figured out before computers were a thing. And so before computers, you would always have to make linear plots because it's very hard to figure stuff out from curves if you're hand drawing it. But you can draw a line pretty easily. And so what you would do is you would make a plot, and your plot would be the natural log of pressure divided by 1 over temperature in Kelvin. And you would get a straight line. And the slope of your line is equal to negative delta H vap divided by R. R is our friend, the gas constant. You might remember R from such equations as PV equals nRT. The ideal gas law, it's the same R. And so what people did back in like the 20s and 1920s, I gotta specify now, is that they would sit in their labs and do this experiment for different liquids. And to get delta H vap, you would take your negative slope. So you take whatever the value of your slope was, stick a negative sign in front of it, multiplied by R. And R R has a lot of values, but the R you use is 8.314 joules per mole Kelvin. You don't need to memorize that value. I would always give you R. But you do need to know for, by the way, this is called the Clausius. Make sure I spell their names right. Clapeyron. I'm probably pronouncing his name wrong. Clausius-Clapeyron equation. You do need to know how to analyze this type of plot. So I could see myself giving you this graph, telling you what the slope is, and then asking you, what's delta H for me, please? Right? And all you do is what I have right here. You take your slope, whatever the value of your slope is, put a negative sign in front of it, multiplied by R. And since this is fair game for something I might ask you, here's how you might see it. So this would be an example question that you could totally see. I give you a plot that is the natural log of pressure over 1 over temp. And I would have like real numbers here. Right? Yada, yada, yada. I would put a line here, and I would say the equation of this line is y equals negative 1343.7x plus 7.399. I would also say R is 8.314 joules per mole Kelvin. And so the question would be, what is delta H? And I'm going to allow you to try that. So given this information for this question, please tell me what the value of delta H is from this plot. Give you a few minutes to do this. Let me know if you have any questions. This is a very powerful skill, looking at plots and getting information from it. So that's why we're working on it. The unit of the slope, let me see. So it's rise over run. So it would be like, it would be Kelvin. Yeah, it'll just be, it's a weird unit. It would be like Kelvin, because natural logs don't have units. So this is unitless. Natural log of P is unitless. And so your slope is just K as a unit of Kelvin. Sinus delta H back times 1. Oh, right. No, now they're ready to divide by that. Yep. All you need is to put number one. And on. What's the first number? What is yours? And so you want to rearrange this equation to be properly. That equals the negative calculation. So we don't know that. That's what we're trying to figure out. So that's a variable. That's it.
So.
That's right. Because you want to get R out of it, you want the variable
Yes. So that's how it's.
negative. Because you have another time stuff on this path.
Yes. So I got rid of it.
Oh, yeah. That's why I don't think it's
And that's this stuff.
Ah. Oh. Also, I mean, that's fine. Yeah, that's good. I really. Or not, or not.
Maybe next week. Let's make.
All right. So